nothing is sustainable in this world, so in order to be practical, we need to define sustainability in relative terms. So the definition I'm using for sustainable energy, it is a source of energy that will last long enough for an innovative technology to provide a replacement, while its impact on the environment can be reasonably managed. Well, this implies R&D to ensure, of course, that the next innovation will come on time, and the research, yeah, I'm not using it, so thank you. And of course, that research effort must include some level of fundamental research, as you all know that fundamental research is what drives innovation. Now, investing in R&D doesn't only mean investing money in R&D, it also means having people able to do R&D, and this means that we must also invest in education. In other words, sustainability requires education. I had prepared a few slides of motivation for the work I'm going to present here, but Professor Xu already discussed all this very nicely and very clearly. So let me just state that we have every reason not to burn fossil fuels until the end of supply. One reason is global warming. The other one, which is an immediate, real, and very costly major problem, is air pollution. In fact, the European Environment Agency stated that air pollution poses the single largest environmental health risk in Europe today. And we're all familiar with those pictures of China with pollution. However, when the wind blows from Germany in Europe, Paris starts looking like Beijing at some times. So this is an issue that is everywhere in the world. It's very costly in money. Europe spends more than 40 billion euros in healthcare expenses related to air pollution. A lot of people die, and in fact, WHO estimated that 1 death in 8 in the world is due to air pollution. That means that 30 people die every day of air pollution. So you would think that this is at least as much of an incentive for doing away with the fossil fuel as global warming. And by the way, there are perhaps better ways of using some of the fossil fuels to manufacture things instead of burning them. Well, if you look at the energy mix in the world primary energy consumption and realize that fossil fuel in 2015 still represented 86% of the whole mix, you can really imagine how huge a challenge it is to replace fossil fuels. However, seems that I forgot one slide, sorry. So, however, those fossil fuels are cheap, abundant, so the current tendency is still to increase the consumption. This is what data extracted from the latest BP statistical review. And, okay, let me skip this. So, the solution must come from R&D, and R&D must be systematic. In particular, it must not exclude nuclear fission domain. Nuclear fission energy has a lot of qualities. It's abundant, it's energy intensive. I remind you that if you want to sustain 1 gigawatt of electric power for 1 year, you can do that with 1 ton of thorium, for example, but you need 3 million tons of coal. And nuclear energy can ensure baseload electricity production. It emits no greenhouse gases or air pollution. It could be made sustainable. Remember my definition of sustainability. So if it were not for accident, waste management, proliferation issues, clearly nuclear energy would be ideal. So the question we should ask is, can nuclear energy be made acceptable to society? The present nuclear energy technology, I remind you, was not chosen to be acceptable. The uranium fuel cycle was chosen in order to produce plutonium for nuclear bombs, and the pressurized water reactors were invented to fit on a boat. So the question is there a better way of exploiting nuclear energy? And a number of physicists think that one answer to this is thorium fuel in fast neutron accelerator-driven system, so-called ADS. Let me make a short comment on nuclear waste. Regardless of national policies, whether countries like Germany wants to stop their nuclear programs, or countries like France want to continue their nuclear program, or developing countries want to start a nuclear program, the issue of nuclear waste has to be solved. The added requirement of retrievability of the nuclear waste makes geological repository strategy at least more complex, if not questionable. On this graph here, you have the predicted evolution of one component of the nuclear waste, the transuranic component, which is the long-term component, between all the way to the year 2050, showing that if you only assume the existing nuclear power plants and those which will be commissioned by 2035, then the inventory of this type of waste will have to double. Now, if you were to produce the whole energy of the world with nuclear systems like the one we have now, then you would have to increase all these by a factor 20. Now, to give you an idea of scale, 6,000 tons of TRU, that represent a lot of power. You can drive 6 power stations of 1 gigawatt electric for 1,000 years. So it's represent a very large potential. And the idea is to use thorium fuel to destroy a large part of this waste. Well, thorium is an interesting element. It has excellent physical properties, better properties than uranium in terms of melting point, thermal conductivity, smaller expansion coefficients, which if you want to manufacture fuel with it, implies a higher margin for design and operation as nuclear fuel. It's abundant, is 3 to 4 times more abundant than uranium, and it's broadly distributed in the world, which has obvious geopolitical advantages. The known and estimated resources are about 6 million tons. Just to give you an idea, we could power the 2.5 terawatt of electric power used by our civilization today for 2,500 years. So this what led Carlo Rubbia at the Tech 13 conference at CERN to state that thorium is in fact a source of energy essentially sustainable on the human time scale. Now, how do you use thorium? Unfortunately, thorium does not fission, so you have to transform it into uranium-233. This is what we call a breeding process. You put thorium in a neutron flux, and then you can produce uranium-233, which produces energy. It's a slight inconvenience, but as you will see later, it can be turned into an advantage. This breeding process is very similar to what is being prepared in generation 4 of power stations, breeding plutonium-239 out of uranium-238. Now, you can imagine that you can use essentially all the thorium and turn it into uranium-233, which can be compared to what is happening now with the PWR power stations, where only the 0.7% of the natural uranium is used as fuel, that is uranium-235. So you have a potential gain of a factor 140 between thorium used this way and U-235. If you convolute this with the larger abundance of thorium, a factor 3 to 4 more than uranium, you have essentially a potential factor 500 more abundance in thorium compared to U-235. Here is a complicated plot. You only need to know that what is plotted is the number of neutrons produced per neutron absorbed in the system as a function of neutron energy. And since 2 neutrons are needed to sustain the fission process, one for capture on thorium and one for fission on uranium-233. In order to breed uranium-233, you need this number eta to be larger than 2. And all you have to remember from this plot is that the most favorable area for doing this is the so-called fast neutron part of the spectrum, the high neutron part of the spectrum, where you can see that uranium-233 is almost as good as plutonium, and actually uranium-235 is rather bad. So breeding U-233 is most efficient with fast neutrons. If you put thorium in a fast neutron flux, this is what you get, a long chain of elements that are produced going to the right through neutron capture, and you can immediately have an intuitive understanding of why the waste production is much smaller with thorium. To go from thorium-232 to uranium-238, you need 6 consecutive neutron capture, and that means the probability to get there is very small, and that means that the production of these transuranic elements is much smaller than in uranium fuel, where you are dominated by the presence of uranium-238. Now, for similar reason, the production of plutonium is essentially negligible, and that makes the thorium fuel cycle proliferation resistant. How do you use thorium in practice? Unfortunately, you cannot just exchange uranium fuel by thorium fuel. First of all, because you need breeding, and second of all, because of neutron inventory issues. So there are 3 basic options. One is to use thorium blanket around a fast critical reactor to breed uranium-233, extract this uranium-233 and use it as fuel in new critical reactors. This is the strategy that has been adopted by India. It certainly works from the technical point of view, but it requires maintaining 3 different reactor technologies at the same time. It's not sustainable because you need uranium to start the process, and it doesn't address the issue of waste. Another possibility is to continuously move the fuel in such a way that you always have fresh fuel in the system, and this is achieved in pebble bed reactors and in molten salt reactors, both of which have severe safety issues to resolve, and in addition do not allow, at least for the moment, to work in a fast neutron spectrum. There is also traveling wave reactors, but they still have a long way to go. In that case, it's not the fuel that moves, it's the breeding and fission wave of neutrons that moves across the fuel. And the third possibility is to provide an external neutron source to palliate the deficiency in neutrons to maintain the chain reaction, and this is what is called accelerator-driven systems. Now, the idea of using an accelerator to produce neutrons is not new. It was proposed at the same time by Lawrence in the USA and Semyonov in the USSR in 1940, and in fact attempts were made to do what we're trying to do today, but the accelerator technology was not ready for that, so those efforts were abandoned. You have here on the right-hand side the principle of an accelerator-driven system. The proton beam is inserted from the top. It interacts with, for example, lead, which has a nucleus which is neutron-rich. So the energy of the beam is sufficient to break the nuclei and produce neutrons, which then can travel all the way to the core surrounding the spallation region, where they can fission, produce neutron, and breed U-233. This is the principle of ADS. The major difference between this type of system and critical reactors is that the reaction is not self-sustained. You need the neutrons brought by the accelerator to continue the reaction. We call this subcritical system. So since it's subcritical, as soon as you stop the beam, you stop the reactions, and therefore criticality accident cannot occur. The added advantage of having an accelerator is these neutrons brought by the accelerator give you a lot of flexibility in the choice of fuel. And for instance, you could mix some of the waste that I mentioned earlier with fresh thorium and use it as fuel. Since in a fast neutron flux, this waste that has accumulated in thermal neutron systems can fission. You can indeed produce energy while destroying the waste at the same time. So the basic concept of ADS were very carefully validated in the 1990s, especially at CERN. There are two pioneering experiments, FIT and TARC, that were done at the CERN PS. So there is absolutely no unknown in the conceptual design of such system. And nowadays we have a very powerful proton accelerator. This is a photograph of a cyclotron that is in operation at the Paul Scherrer Institute in Switzerland, which runs at a beam power of 1.3 megawatt, and today designs exist to reach a power of 10 megawatt. We need to ensure a spallation process, and a lot of progress has been made also in this area. The first spallation system to reach 1 megawatt was the MegaPi, also at the Paul Scherrer Institute. It was run as an experiment in 2006. Nowadays, we have the spallation neutron source at Oak Ridge in the USA that is running routinely. It has reached 1.4 megawatt on target. And Europe is constructing at Lund in Sweden the European spallation source that will reach 5 megawatt on target. So essentially, today we have the technology that we need to start industrial system. There are three major programs in the world concerning ADS. The most advanced one is MIRA. This is happening at Mol in Belgium. It consists of a LINAC which feeds a 2.4 megawatt beam into a subcritical core which is cooled with a lead bismuth eutectic coolant. In principle, MIRA should be the flagship of ADS project. However, it's only partially funded, and this is really a shame in my view if you consider, for instance, that in Europe between 2005 and 2013 the EU spent 600 billion euro on renewable energies, most of it on subsidies. So had they spent only 599 billion euro and given MIRA 1 billion, I don't think that would have done any damage to renewable energies, but it would have tremendously advanced the field. So we don't know for sure when MIRA will be able to operate, because right now it is not yet funded. There is no thorium in the plan, and after a few years, couple of years of operation, MIRA, the accelerator will be removed to do something else, and MIRA will be transformed into a critical reactor. The next very important program is in China. It's called ADANES. It's a complete energy system with the ambition to produce 1,000 megawatt of electric power by 2032. The first stage consisted of building two injectors with two different technologies, and in China everything is done in a very efficient way, so two different laboratories are actually competing to do this, and in the end the best solution will be chosen. Last December, the central government approved the second phase of this program until 2022. And what is really very interesting when you discuss with the people involved, in particular with Wenlong Zhang from the Chinese Academy of Sciences, is that the approach is to be innovative, and they are studying ideas on the fuel cycles and new ideas on the spallation targets. They have a system with little grains that circulate with a magnetic pump, etc. And even though it will take a long time, I'm sure that China will succeed. There is a program also in India, which is actually coming from initiative at Fermilab. That was a project called Project X, which was to build a 1 GeV LINAC with a power of 10 megawatt. And now this project has been carried out to India, and this is the third major project on ADS. ITEC, the association which I represent, is a non-profit association situated in Geneva, and its goal is to promote R&D of thorium. And ITEC realized that since there is a very long time scale for these two programs I mentioned, MIRA and China, we could perhaps do something useful in the meantime. And we discovered that in the Moscow area, an infrastructure exists that would allow to couple for the first time a beam to a subcritical fast neutron system at significant power. Significant power means a few megawatt. And indeed, at Troitsk, you have a LINAC, which can go to 600 MeV. You are in operation neutron spallation source, which is used to produce radioisotopes for medicine. And there is a beamline which is available, and even a pit and all the infrastructure for that. And if the funding is found for this in 5 years and less than 4% of the cost of MIRA, we could characterize all the properties of ADS. And when you go to a fast critical core, scaling laws can apply to then design an optimum industrial system. So we are at this time looking for the funding to prime the pump, if you wish. The second initiative of ITEC is the development of an accelerator which is optimized for our application. We want to design an innovative cyclotron. It will be a one-stage, that means very compact cyclotron, 600 MeV, 6 milliamps, so a reasonable power, 3.6 megawatt. This is the baseline. We do not exclude going to a higher power, but the design concerns are to get the highest possible reliability through redundancy. In this special case, we have enough room to have 3 injectors, high efficiency and lower cost. I mean, we have reasons to think that the cyclotron solution will be cheaper than a LINAC. So a proposal will be submitted in the EU in the Horizon 2020 program in January, and this is a collaboration between CERN, Paul Scherrer Institute and IMA. Paul Scherrer Institute and IMA are 2 of the world experts on cyclotron, and there is also Ansaldo in Italy and a couple of other industrial companies. A last comment I would like to make is this development of a high-power accelerator can open the field for other applications, in particular the production of new alpha emitters for medicine, which require relatively higher energy and also higher beam intensity. So let me conclude by saying that arriving at a zero-carbon society in a sustainable way requires innovation, hence a systematic R&D effort, including nuclear fission energy. The fast neutron accelerator-driven systems using thorium fuel offer the possibility to transmute a major part of the long-lived nuclear waste and produce energy. Therefore, that explains the title of my talk. Thorium is a potentially sustainable source of energy for the future, and the development of accelerator for these type of systems can bring further benefits to society, in particular in the medical area. Thank you very much for your attention.